So we are seeing this note. So integral if phi is equal to 0 almost everywhere, equal to 0 wherever we can write it as greater than or equal to 0 and less than or equal to 0 almost everywhere. So this happens when so both simultaneously happens when phi is equal to 0. For greater than or equal to 0 almost everywhere ആണെങ്കിൽ by the result we have seen previously, integral over phi greater than or equal to 0 ആയിരിക്കും. So similarly, if phi is less than or equal to 0 almost everywhere, so integral phi will be less than or equal to 0. Again, both will happen simultaneously. Now both are possible simultaneously only if integral phi is equal to 0. So therefore, if phi is equal to 0 almost everywhere, then in that case integral phi will be equal to 0. Now we look at the next proposition. So this proposition is analogous to result we have seen in Riemann integration. For Riemann integration നമ്മൾ ചെയ്യുമ്പോൾ നമുക്ക് ലോവർ ഇൻറ്റഗ്രലും അപ്പർ ഇൻറ്റഗ്രലും കിട്ടും. ഒരെണ്ണം സുപ്രീമം വരുന്ന വാല്യൂ ഒരെണ്ണം ഇൻഫേം വരുന്ന വാല്യൂ. സോ പ്രൊവൈഡഡ് ദ ഫംഗ്ഷൻ ഇസ് Riemann integrable, the lower Riemann integral will be equal to the upper Riemann integral. So similar result holds in the case of Lefebvre integral for simple function. So let us see the analogous result. So the proposition states that so if f is defined and bounded on a measurable set E with measure of E less than infinity, so E has a finite measure, then supreme over phi less than or equal to f, integral over E phi of x dx will be equal to infimum over xi greater than or equal to f, integral over E xi of x dx for all simple functions if and only if f is measurable. So if f is measurable, then the supreme over phi less than or equal to f, integral phi will be equal to infim over xi greater than or equal to f, integral over E xi. So we will prove in both ways. So first, if f is measurable, we will show that supremum value will be equal to the infimum value, and the opposite way also. Supremum equal to infimum angle, we will show that f is measurable. So we will now look at the proof of if f is measurable, then the supremum is equal to infimum. So this is what we need to prove. So let us call that as equation A. So supremum over phi less than or equal to f, integral over E phi dx less than is equal to infimum over xi greater than or equal to f, integral xi dx. So we need to prove this. Now you are given that f is defined and bounded on a measurable set E. അപ്പോൾ എഫ് ബൗണ്ടഡ് ആണ് ഓൺ ഇ. അപ്പോൾ എഫ് ബൗണ്ടഡ് ആണെങ്കിൽ ദാറ്റ് മീൻസ് എഫിൽ അറ്റൈൻ maximum and minimum value on E. So let us say that f lies between the values minus m and m. So you can find an m such that modulus of f is less than or equal to m for all x belongs to E. So that's the definition of a bounded function. So function bounded angle, you can always find an m such that f lies between minus m and plus m. So we have got such an m where f lies between minus m and m. So we have this interval minus m to m. ഇതാണ് നമ്മുടെ interval minus m to m. Okay. Now let me define now a sequence of functions E defined as follows. Okay. അപ്പോൾ അതിന് ഞാൻ m minus m ഇവിടെയുണ്ട്. So let me take the value minus m minus m by n. Then on the right side we will have minus m plus m by n, and from m you will have m minus m by n. So we are taking intervals of length m by n, covering the interval minus m to m. So this is how we are going to define the sequence Ek. So let us define for k varying from minus n to n, ek to be the set of all x belongs to E such that k minus 1 by n into m less than or equal to f of x less than or equal to km by n. So let us define ek by set of all x such that km by n minus m by n less than f of x less than km by n. So those are these intervals. ഈ കാണുന്ന intervals ആണ് നമ്മുടെ ek എന്ന് പറയുന്നത്. So e minus n will be when k is equal to minus n, we will get m minus m minus m by n varum less than fx less than minus n varum. So that will be this first interval. This will be e minus n. Then e minus n plus 1 will be so here minus n plus 1 varum. So that will be again minus m minus n varum to so minus n less than fx less than so k m by n. On the right side we will have minus n plus 1 m by n. So this will be minus n plus m by n. So this is the next interval. E minus m minus m plus m by n. So this is e minus n plus 1 and this is e minus n plus 2. So on the last interval will be en. So en, you can see that en will be so en by the definition en എന്ന് പറയുന്നത് n minus n by n to ഇവിടെ k യുടെ value n വരുമ്പോൾ you are going to get m. So that is m minus n by n to m. So this will be the interval en. Now we have e minus n as set of all x such that f lies between minus m by n to minus m. So that will be f inverse of minus m by n to minus m. F inverse in the value ആയിരിക്കും. We need the set of all x such that f lies between this interval. So that will be the corresponding inverse function the value ആയിരിക്കും. So we can write all the sets in the terms of inverse functions. So e minus n plus 1 will be f inverse of minus m plus m by n, and en will be f inverse of m minus m by n to m. We know that f is measurable by the property of measurable functions. So if f is measurable and e is a Borel set, then in that case f inverse of e is measurable. F measurable ആയിരിക്കണം, e Borel set ആയിരിക്കണം. e in this case here e minus n തുടങ്ങി en വരെയുള്ള intervals ആണ്. So they are going to be Borel sets. So they are measurable. So intervals ആണ്, measurable ആണ്. So f is also measurable. അങ്ങനെയാണെങ്കിൽ by a result f inverse of e will be measurable. So we can conclude that all EKs are measurable. So all the EKs will be measurable. Now E can be written as so here e minus n plus 1 en. So all are disjoint and E can be written as en k equal to 1 to n ek. Function actually defined ആയിട്ടുള്ള set ആണ് E. Now by ek you mean we are finding the set of all x belongs to E such that f lies between that particular interval. Minus m to m എന്ന് പറയുന്ന ഇന്റർവലിനെയാണ് നമ്മൾ ഡിവൈഡ് ചെയ്തിരിക്കുന്നത്. അപ്പോൾ അതിൻ്റെ അകത്ത് f എടുക്കുന്ന വാല്യൂസ് ഏതാണോ അതിൻ്റെ inverse image. So we are finding set of all x such that f takes a particular value in the interval. So we are going to get all the values in the set E. So therefore, E case എന്ന് പറയുന്ന disjoint ആയിരിക്കും and their union will be equal to E. So therefore, E will be equal to union K equal to minus n to n Ek. Now by the additive property of M, so measure of E will be summation K equal to minus n to n measure of Ek. Now let us now bring functions phi and xi. അപ്പോൾ നമുക്ക് prove ചെയ്യേണ്ടതാണ് supremum of set of all phi less than or equal to f integral phi. So this must be equal to infimum over all xi greater than or equal to f integral over xi. So we need to bring this functions phi and xi. അപ്പോൾ നമ്മൾ ഇവിടെ നമ്മൾ ek എന്ന് പറയുന്ന സെറ്റ്സ് ഡിഫൈൻ ചെയ്തു. അപ്പോൾ ekയിൽ the function lies between these values k minus 1 by n m and km by n. So using these values km by n and k minus 1 n by n to define simple functions phi n and xi. So we'll define phi n as follows. So phi n is a simple function defined on E such that it takes a value k minus 1 n by n on the measurable set Ek for k equal to minus n plus 1 etc. n, and xi n will define it as a simple function which is taking the value km by n on the measurable set Ek. So ഓരോ E കേസും disjoint ആണ്. So on Ek phi n will be taking this finite value. So phi n and xi n can be represented in the canonical form as follows. So phi n will be summation k minus 1 m by n chi of Ek, and xi n will be k m by n chi of Ek. Now integral of phi n will be canonical representation, that will be integral phi n will be summation minus n to n k minus 1 n by n m of Ek, and integral of xi n will be summation km by n m of Ek. Now we know that f of x lies between k minus 1 m by n and km by n. So phi n and xi n will be such that so phi n will be less than or equal to f of x will be less than or equal to xi n, and this is true for all k. So we have this inequality phi n of x less than or equal to f of x less than or equal to xi n of x for all x, and we have this integrals. So when you take supremum over phi less than or equal to f integral over E phi of x dx, ഇനി ഈ supremum എടുക്കുമ്പോൾ supremum will be greater than each phi n. ഓരോ phi n നെക്കാളും വലുതായിരിക്കും supremum over all phi less than or equal to f integral over E phi of x dx. So supremum will be greater than or equal to integral phi n x dx. ഇനി integralന്റെ വാല്യൂ നമുക്കറിയാം, that will be summation minus n to n k minus 1 m by n into m of Ek. Okay. Similarly, infimumത്തിന്റെ കേസിൽ infimum ഏറ്റവും ചെറുതായിരിക്കും and all the integrals in's will be greater than or equal to the infimum. So infimum over xi greater than or equal to f integral over xi of x dx will be less than or equal to integral xi n, and integral xi n ന്റെ വാല്യൂ എന്ന് പറയുന്നത് minus n to n km by n m of Ek. Now take the difference of this infimum and supremum. So infimum minus supremum will be less than or equal to അപ്പോൾ നമുക്ക് ആ കിട്ടിയ സമ്മേഷന്റെ വാല്യൂ കൊടുക്കുക. So upon taking the difference we will be getting km by n minus km by n plus m by n വരും. So the difference will be m by n m of Ek. So your difference this holds for all n. So it will hold for n approaches to infinity also. Okay. So നമുക്ക് difference m by n into summation is upon k. അപ്പോൾ m by n പുറത്ത് വരും. m by n summation minus n to n m of ek വരും. And m of ek, so summation k equal to minus n to n m of ek എന്ന് പറയുന്ന m of e ആണ്. കാരണം നമ്മൾ ആദ്യം പ്രൂവ് ചെയ്തായിരുന്നു e will be union of k equal to minus n to n. ek again disjoint ആണ് ek, so measure of e will be summation measure of ek. So this will be equal to measure of e. Now measure of e finite ആണെന്ന് തന്നിട്ടുണ്ട്. So this will hold for all n. So it must hold as n tends to infinity also. So as n tends to infinity, this value approaches to 0. So therefore infimum over xi greater than or equal to f integral xi minus supremum over phi. This must be equal to 0. So we will get supremum equal to the infimum. So that is the proof of the first part. So in the next lecture we will look at the proof in the other way. So when you are given supremum equal to infimum, we show that f is measurable.